Today, we're very pleased to have Jane Gao, who is a faculty member in CNO and works in graph theory, theoretical computer science, probabilistic method, and so on. And today will tell us about symmetry of random graphs.
Thank you, David. So I'm very happy to talk about it's not really recent work anymore. So this work has been done about 3 years ago, but it just takes us time to actually write it down and put it online. So it only appeared a few months ago. So this is about symmetry of random graphs. And it's collaboration with Lachlan Brick and Angus Southwell. So they are my students back in Monash University. Lachlan was an honors student, so honors degree is somewhat like between the 4th year undergraduate and the master degree, somewhere in between, because we're only 3-year undergraduate studies in Australia. And Angus was my PhD student. So in fact, this work was actually initiated by Lachlan when he approached me and wanted to do an honors degree with me. I had some plan for him, but then he just said that he wants to do something about the graph isomorphism. But since there are already very strong results there, and I told him that I don't really know so much about graph or algorithms on isomorphism testing, but if you would like to do something related to it in random graphs, maybe there's something we can still do. So then we started to search for papers and see what can be done. And we came to this paper. So it's about the automorphism group of random graphs with specified degrees. There was a title there was a typo in the title. So this result is a bit old. It's 1984. And when I look at the paper, I feel that something can be improved. So we started to study this paper, and in the end, we improved some part of it. Okay, so I'm going to tell you a little bit about this story and what we do and, what we did. So here's a brief outline. So I'm going to introduce automorphisms. They're not isomorphisms, but they are close enough to be in the morphism group. And then I'm going to talk about the random graph models we are going to use today, introduce some known results and also what's new, and a quick and a brief overview of the proof techniques. And in the end, I will talk a little bit about further the future work or further discussions. Okay, before the talk starts, and just the way that I give talks, I always like to give some convention of the talk. So the graphs that we are going to talk about today, they are all vertex labeled. So only labeled graphs, they are all defined on the same vertex set that is 1 to n. And whenever there's a C that appears a constant, that just means certain statement holds for some appropriate constant chosen there. So it holds for some constant. Whereas if there's some epsilon there, it's also constant, but usually the statement is that it has to hold for all sufficiently small constant. Okay, so epsilon represents some small constant and the C represents some constant that doesn't matter. Random variables in this talk, I will try to preserve the red color for it. So when you see a red, you know it's random graph or random variables. So what is automorphism? I guess everyone knows it, but I think as a talk, I would like to include the definition as well. So I'm given a graph G defined on the vertex set N, and you are given a set of edges denoted by A. And also given sigma, which is a permutation on n objects. I can define this sigma star, which is also a permutation. It's a permutation of the set of edges in the complete graph. So basically it's defined by any pair of vertices, this sigma star mapped to the pair of vertices on the sigma. Okay, so it's just sort of like when you move the vertices in your graph, it moves the associated edges in the graph as well. So now I can define G sigma to be it's like a sigma acting on G. So it's on the same vertex set, but the edges are the set of edges in G moved under this sigma star. Okay, so the automorphism group of G is defined to be the set of permutations sigma such that under this permutation you get the same graph, G equals G sigma. And always the identity permutation would always be in the automorphism group because if you don't move anything, you get the original graph. Okay, just to show a few examples to illustrate the idea. So here you have a you have a graph on 5 vertices, and clearly this graph is symmetric. If you swap A and B and C and E, swap means just by relabel those vertices, then you get back to the original graph. It's the same graph, the same vertex label graph. So you have an automorphism that is not the identity permutation. So in that case, we say G is symmetric. And in the other case, so here, this graph also has 5 vertices. And if you want to find a permutation that's still, under the permutation, you still get the same graph, then obviously you want to preserve degrees. So D has to be mapped to D, and maybe A, C can be swapped, and maybe B, E can be swapped, but if you check those possibilities, you will see that under none of those, you will get the same graph. So the only automorphism in this case is the identity permutation. So in that case, we say G is asymmetric. So all the definition clear? All right, so we are going to study the automorphism group of random graphs. So let me introduce some random graph models. The most well-known one is the Erdős-Rönni graphs, GNP and GNM. So GNP independently selects an edge in the complete graph with probability P, whereas GNM is the uniform model on the set of graphs with M edges. Okay, and sometimes we want to consider these kind of probability space. I have put K here. K is some positive integer. That means that you are considering GNP, but with the condition that the minimum degree is at least K. Why are people particularly interested in this kind of probability space? Well, sometimes it's just try to make this, in some sense, try to make your problem a little harder. So for instance, if you are thinking about the symmetry of random graphs, the problems start to become interesting only when P is about the logarithmic size of n over n. In the other sense, yeah, M is, so average degree is about log n. Why is that? Because before, when P is smaller, then there are a lot of isolated vertices in the graph. So trivially, you will have you have symmetry. You can always swap isolated vertices. So you will only study graphs when the density is already over log n. So if you want to make it a bit more interesting, you can say, okay, if it's the isolated vertices that are making problem easier, why don't we just restrict the degrees to be at least K? And so that's one of the typical, one of the reasons that people are interested in this type of random graphs. But there are other reasons as well. Well, the other random graphs that we care about, G and D, is the uniformly random G-regular graph on the set of vertices 1 to n. So if you want to make the problem even a little harder, you can think about this probability space. You don't have edge independence anymore, and in G and M you can compute probabilities of events fairly easily, but in G and D it's no longer easy to even consider the probability of a set of edges appearing simultaneously. And if you want to make it even harder, you can specify a degree sequence D, this D tilde, and then think about a uniformly random graph with that degree sequence. Okay, so in other words, it's a uniformly random d-factor of the complete graph. So going from G and D, well, this is a generalization of G and D where every component is equal. But going from here to here, so even if you pick up just a pair of vertices and ask what's the probability there's an edge there, it becomes non-trivial already. All right, so a bit more convention of the talk. So we are going to talk about probability spaces. So even so, we say that graphs are defined on the set of vertices from 1 to n, but eventually we are going to think about the sequence of a sequence of random graphs where n is, the sequence is indexed by n. Okay, so n can go from 1 to 3 and forwards. And in each probability space Gn, you can define some events, say En. For instance, En can be the event that a random graph Gn is symmetric, okay? And then you also get a sequence of events. So we typically care about asymptotic behavior of random graphs or events in random graphs, and the asymptotic always refers to n goes to infinite. And then we use the notation WHP to denote with high probability. So if for some events, the probability of that event occurring goes to 1 when n goes to infinite, then we say this event occurs with high probability. And I also use omega 1 to denote a function of n that goes to infinite as n grows. Okay, so what is the phase transition in GMP in terms of symmetry? This is a theorem by Wright in 1971, basically characterize where this phase transition occurs. When P, well, in fact, what I want to say is symmetry is a property that's certainly, you know, if G is symmetric, then so is the complement. So you only have to think about P up to a half. And that's why there's a main function P and 1 minus P there. So if we just think about P only go to a half, then when P is above log n over n, then G is asymmetric. And when P is below log n over n, then G, with high probability, G is symmetric. So the phase transition occurs at the time when P is about log n over n. All right, and a bit of a history of this result. So the special case when P equals a half was given by an earlier paper by Ehrlich and Rennie, 1963. That's just the 3-4 years after the introduction of the random graphs. And in the same paper, they actually claimed the same results here that they say would appear in a subsequent paper, but I think it didn't really appear. And then in the Wright's proof, what they actually proved is that they checked, well, they computed the expected size of the automorphism group of GMP. In the asymmetric range, they show that this is 1 plus little 1. So this 1, of course, represents for the trivial automorphism, the identity map. And so all the non-trivial, basically what it says is in expectation, you don't see any non-trivial automorphisms. And this result immediately gives, actually gives you the number of unlabeled graphs on n vertices and m edges. So what Wright says is once m exceeds some critical value, then random graphs are asymmetric. So you can easily compute the number of m-edged graphs, vertex labeled graphs. Well, that's just the among so many edges, you choose m edges, right? And then with things with high probability, in expectation, there are no other automorphisms. So immediately you divide it by n factorial, you get the number of unlabeled graphs on n vertices and m edges. Okay, so that's just a direct consequence corollary of Wright's result for the study of automorphism group. In fact, actually, his paper really is about counting unlabeled graphs on n vertices and m edges. And earlier than Wright, there was a claim by Polya, claimed the same results as Wright's theorem over here, except the P, he didn't really say, try to say something so general of P of this wide range, but what he wants to claim is 1P roughly is a half, so M is about a half times n choose 2, then the expected number of automorphism group is size of that is 1 plus little 1. But again, that paper also that result didn't really appear. Another result did appear is by Obashev in 1967 with slightly relaxed M. So it's still, again, P is around a half, so about half of the edges of the complete graph. And he showed the same result over here. So much narrow range of M. And then it comes Wright's proof. Okay, so if we look at the result by Wright, we would see that this phase transition coincides exactly with the property of G being connected. So in the regime that G is asymmetric, it corresponds exactly to the regime that G is connected. And in the regime that the G is symmetric, it corresponds to the situation that the G is disconnected. Okay. Okay, there are some other work following that for the sparsal graphs. As I said before, if you know the GMP, somehow it's sort of like the asymmetric case a bit easier. I'm not saying the proof is easy, but if you want to make the problem even harder, you can try to push down the density further. But then there are a lot of isolated vertices. So what you can do is to study what Linear and the Moshaev did is to study the two-core of GMP. So what is that? You take a GMP and then strip off all the vertices of degree less than 2. Keep doing that, and then eventually you reach a subgraph with minimum degree at least 2. Another way to think about is just take GMP conditioning on minimum degree at least 2. They are not the same thing, but they are almost like the same thing, at least for this problem. So now you are allowed to actually think about the P that is smaller than log n over n. So what they studied is 1P is below log n over n, but still much bigger than 1 over n. They show that this random graph is asymmetric. And it's quite easy to show that 1P is below this range. It's not going to be asymmetric. It's actually going to be symmetric with a non-trivial probability. Yeah, I think so. Okay, so that's one. And the other is, why do we study in GMP? We can make it even harder. So why don't we study it in random irregular graphs? In some sense, if you want to study the automorphism group of random graphs, maybe the natural thing is to think about the random regular graphs, because all the degrees become the same. So potentially it's possible that every vertex can be mapped to any others, because the mapping has to preserve the degrees. So when D is either 1 or 2 or n minus 2, n minus 3, it's very trivial that this random graph has to be symmetric. D equals 1 is just a perfect matching, or yeah, perfect matching. D equals to 2, the random graph is just a bunch of cycles, so of course they're symmetric. And starting with D at least 3, Bolobos showed that it's with high probability it's asymmetric. And the proof only works for bounded D, so D doesn't grow with N. McKay and Wormold get the result when D goes to smaller order of square root of N. And then finally, 2002, Kim, Sudakov, and Wu proved all D. So all the D that's not included here, they show that the random D regular graphs are asymmetric. So in other sense, random D regular graphs are asymmetric except in trivial cases. Okay, so how about random regular graphs with a specified degree sequence? So that was the paper that I showed you in the beginning of the talk. And in fact, this result, particular result here for the D regular case, come from that paper as a special case. Okay, so it's this paper. So what they did in this paper is they didn't really try to catch when, like the phase transition of G and D being symmetric or asymmetric, but they just try to give sufficient conditions under which this random graph is asymmetric with high probability. So this is their main result. And there's by no means that I would like you to actually understand or try to digest what it tries to say, but I'm just going to give a few words and then telling you that what kind of results they are saying, this main theorem. Okay, so you are given a degree sequence D, I wrote it here, and then you take the class of graphs with that degree sequence D, and this is this S, so the thing here. So that's the class of graphs with that given degree sequence. There's some kind of technical definition f of n, but for D, that's nice enough. You can just think about f of n being some constant times maximum degrees, square of maximum degree over this is average degree. So delta is the maximum degree, D bar is the average degree, and little delta is the minimum degree. Okay, so in the first statement, it says something about the one, the minimum degree is at least 3, right? Here's at least 6, here's between 3 and 5. And then under some constraints involving f and n, so if you put f, if you replace f by this thing, it tells you some kind of constraint of the degree sequence regarding the maximum degree and average degree and n. Okay, and then under such constraints, then they show that Tn is this quantity. What is Tn? Tn is the expected size of the automorphism group of G minus 1. So in other words, it's the expected number of non-trivial automorphisms. And then it's expressed under using some kind of formula, but then if you replace f of n by this thing, you can work out another constraint to make Tn little of 1. So that says that under those technical constraints over here, then you know that the expected number of non-trivial automorphism is 0. Okay. And then the condition, this second part specifically deals with cases where there are vertices with degree 1 or 2. So n1 is the number of vertices with degree 1, n2 is the number of vertices with degree 2. And again, with some kind of constraints here, they say when under what kind of constraints there won't be any non-trivial automorphisms. But if I just rewrite some kind of corollary of this theorem, it becomes much more readable. So one is this G and D asymmetric. Here are some corollaries. First, you check the D regular case, then they can show for the D in the range between 3 and n to the, roughly speaking, square root of n. And if you think about the bounded degree sequences, so the maximum degree is bounded, it doesn't grow with n, then you can think about any bounded degree sequences. As long as the minimum degree is at least 3, they also show that this random graph is asymmetric. And the other case is under some mild constraints here for delta, something like a square root of n. If the number of degree 1 vertices, so n1 is smaller than n to the third, or if the number of vertices degree 2 is smaller than n to the 2/3, then they also show that this random graph is asymmetric. So what we try to do is that we find this constraint is sufficient but not necessary. In other sense, it doesn't really capture the phase transition of graph symmetry. So we try to improve this constraint. Okay, so
Jane, can I ask a question?
Yeah.
So this Wright's result showed that the phase transition for symmetry is the same as the phase transition for connectivity.
Yeah.
So I have two questions regarding that. Is there a, I mean, is there a, I don't know, a simpler or maybe more direct proof for seeing why those two phase transitions should be the same for G and P? And the second question is, I mean, is that a more general phenomenon in some sense, that maybe that there are other distributions for which you can just show this?
I'll address both of it in this talk.
Okay,
so
great.
You'll probably see that just in a few minutes.
Awesome.
Okay. Okay, so this is our result. So here is a case where you think about the degree sequence where the maximum degree is bounded, just as a simpler version of the theorem. So you take a bounded degree sequence and then take a random graph from given that degree sequence. So what we show is if the number of vertices with degree 1 is little of square root of n, and the number of vertices with degree 2 is smaller order of n, then with high probability, G is asymmetric. On the other hand, if n1 is much greater than the number here, then G is, with high probability, G is symmetric. So this does capture the phase transition. And if n1 is of the order at least n to the square root of n, or n2 is of linear size, then we know that the probability G being symmetric is going to be bounded away from 0. So has non-trivial distribution. Okay, and again, these constraints here, if you look at the condition, they coincide exactly with the connectivity threshold for G and D as well. Okay, and this is the more general result. And again, I'm not going to explain anything about it. I just want to say, because it's too technical, but I just want to say you don't really have to think about bounded degree sequences. You can let delta grow. You can let the delta grow as long as it doesn't grow too fast. And we try to have some sufficient conditions under which it's asymmetric, and also sufficient conditions under which this random graph is symmetric. Okay. Okay, so now we have seen some kind of coincidence between the graph symmetry and the graph connectivity. So for both G and P, and in the case of G and D, where the degree sequence is bounded, then you see that typically if graph is asymmetric, if and only if it's connected. But interestingly, this doesn't really hold in general for general degree sequence D. And we actually cook up an example where you have n1 vertices with degree O1, and then the rest of the vertices with degree log n. And the n1 is chosen in this range. And then using our theorem before, you can actually see that G and D is going to be symmetric, but you can also check that the graph is actually connected in this case. So it's not always the case that when the graph becomes symmetric, it is because it's disconnected. It can happen not, this coincidence can be broken. And now I'm going to explain to you why in some situations or some GMP or some nice degree sequence case, they coincide, and then for general degree sequence, they can not hold anymore. So in short sentence, I can say this way. So random graphs are typically asymmetric. And if they are symmetric for some trivial reasons. In some sense, you can typically find some small graph structures and indicating that the graph is symmetric. So let me define cherries are two vertices with degree 1 that has a common neighbor. Okay, and a pendant triangle are a triangle where two of the vertices are of degree 2. Then isolated edges, an isolated edge is an edge with both ends of degree 1. So these vertices are of degree 1. So yeah, when you have an isolated edge, the graph is disconnected. And you can also define isolated triangle, where in which case all those 3 vertices must have degree 2. Well, so in the GMP and also in bounded degree situation, the graph symmetry were caused by the cherries, okay, or the pendant triangle. But isolated edge also is a way to actually, if you have isolated edge or isolated triangle, they also say this graph must be symmetric. But interestingly, in GMP and in bounded degree sequence case, these two structures appear at the same time. So when cherries start to appear, isolated edge also appear. And the same for here. So if you have a pendant triangle that start to appear, then you also have isolated triangles start to appear. So that just tells you why the symmetry and the disconnectivity sort of happens at the same time. Because, yeah. But when delta, the maximum degree, start to grow, you can actually cook up some kind of degree sequences such that cherries start to appear, but isolated edge doesn't. So the graph can still be well connected, but it becomes symmetric. So that answers Swami's question. All right, so I'm going to quickly, well, in fact, this already gives you the proof of the symmetric case. It's actually very simple. For symmetric case, you just try to prove that certain structure, certain subgraph appear with high probability or with non-trivial probability, and therefore it's symmetric. Very easy proof. And the non-trivial proof is for the asymmetric regime. A natural try is what Brandon, McKay and Wormold, what they did. So you define T of G to be the size of the automorphism group subtracting 1. Okay, so it's the number of non-trivial automorphisms of G. And you try to show the expected number of expected size of T is going to be liter of 1. And that's exactly what they did. So how are you going to compute this expectation? You have to sum over all permutations that are not identity permutation. Then you sum over all graphs H, which has sigma as an automorphism of H. And then you know, this amount here would be the probability that your random graph G is H. Okay, you need to do this. This is by definition. Well, quickly you can actually see that you don't really have to think about edges that are not incident, right? Yeah, incident with vertices that are not moved by this permutation. So in this example, for instance, this permutation moves, swap those 2 vertices, and you know, cyclically map this to this and this to this. This is recycle here. You just need to make sure H is H here. Now I'm just looking at the set of black edges that are incident with those moved vertices, because those blue edges, I don't care, right? They are not affected by the permutation sigma. So I just want to sum over all the graphs H, now only incident with vertices that are moved, and those graphs that are invariant under permutation sigma. Or in other words, you can think this way, take all the graphs, subgraphs in H sigma, and then delete edges that are induced by vertices that are not moved. And that's this class of graphs. And now here is just a probability that this out here should be subset. So regard H as a set of edges. So what's the probability these set of edges are in G? Okay, so the task now is how do we express this probability? And second is how do we sum over those big two summations over here? So the first question is relatively easier. So there is such it comes from enumeration, but it's very easy to, very convenient to apply. So as long as the maximum degree is not too large, you look at the probability that all the edges in H are included in this random graph is bounded basically by square of the maximum degree over total degree of the graph, okay, raised to the number of edges in H. So it's like a product. It's almost like in GMP, right? You just, if you think about here is P, it's like P to the number of edges in H. So in that sense, it's quite convenient to use. Okay, so now the big task is actually doing this big summation. So I'm just going to briefly explain how they did it. They actually, it's hard to count in general, but if I partition this set of permutations and the graph in that class of families of graphs, according to certain parameters, then I can actually get upper bounds on the counting, various counting. So the parameters include the following. I look at support of sigma. Here's just the set of vertices that is moved by, by this permutation sigma. So I'm now fixing sigma and fixing a graph H that are invariant under this sigma. So A of I is the, what is it? The number of vertices that are moved by sigma whose degree equals I. And L is the sum of degrees of vertices whose degree is at least 3 and has been moved by sigma. And then I can also look at, your sigma induces a set of cycles, right? It's permutation. So you look at all the number of I cycles encoded in SI. So the sequence of SI denotes how many pairs of vertices has been swapped with each other and how many 3 cycles and 4 cycles and so on. K is the number of edges in H. E1 is the number of edges in H fixed by this sigma. So that only happens if you have 2 vertices that swap with each other and there's an edge between them. So under this swapping, this edge is fixed. And then the other more complicated situation is an edge somehow, if you look at the set of edges in complete graph, when you act sigma over the set of vertices, you actually induces a permutation on the set of edges in the complete graph, partitioned into a set of orbits, right? And if sigma is an automorphism, that means that if an edge appears in an orbit, then all the edges in that orbit must be filled. So that's another parameter. But anyway, you don't really have to really understand all of those things. I just want to say that I'm going to fix those parameters. So A1, A2, A at least 3 means all the vertices moved that are of degree at least 3, and L and S and K and E1 and F. I fix all of those. And then I'm just going to fix those P, okay? And then I'm going to look at the permutations that are consistent with the set of parameters that I'm given, and look at the subgraphs H that are consistent with this parameter P and sigma. And then this probability is just written as here, because now I know the number of edges in H is K once I fix this P parameter P. And then I can count the number of permutations given the parameter p, right? Because I already know how many vertices of each type I'm going to choose. That's all specified by p, so I can just count those vertices and I think about how to arrange them into groups of cycles. Okay, so I can count those, and I can also count the edge. The graphs there. So something really clever here is, in general, if you want to think about subgraph, you have to put edges in your chosen set of vertices. But now you only have to count the orbits, because once an edge is there, then all the edges in the falling into the same orbit all has to appear. So you save tremendously over here by counting the number of orbits instead of counting the number of edges. Okay, so that's I think the key idea is there. And after this, there's still like several pages of calculations, but eventually, you know, because there's a lot of things to sum over, but once you do all the big summation over here, and under there, that also explains why the conditions are so technical, but then you put it in, you get little one. So this thing has to be replaced by this F thing if you really use their general theorem, but I'm just going to write a simpler form over here. So what we did in the beginning is just try to extend the proof and see if you can get actually go all the way to the threshold of the symmetry, but unfortunately it didn't. So we need to do something new, and I'm just going to briefly explain what new stuff we did. So this is the main result, and I don't want to explain anything about that. Just look at the simpler version where delta is bounded, right? So n1 is little of n square root of n, and n2 is little of n. So what we did is, you look at the set of parameter p over there. I'm going to further partition it into two cases. So take out the subset of p, where the number of vertices that are moved of degree at least 3 is at least 10 times the number of vertices that are moved at a degree 1, and also at least 10 times of the set of number of vertices that are moved that are of degree 2. Okay, so take out these set of parameters p there, and then consider all the other permutations where you don't have so many vertices that are moved that are of degree at least 3 compared with, you know, A1 and A2. Okay, so what we could do is I sum over P bar in Q instead of in Wormhold's and McKay's result that you sum over all, right? I only sum over in this subset of parameters there, so that we were able to actually extend their argument and show that it's little of 1. And that was okay. You need to extend somewhat of the result, but eventually that could be done. So immediately, what it means that it means that the expected number of automorphisms of type that are not in S, that goes to 0. So now I only need to show that with high probability, none of the permutations in S can be an automorphism of G. Here's a quick sketch of the proof. So we can show that with high probability, you take any path in your graph where the ends are degree 1 vertices. Along this path, you must see at least 4 vertices of degree at least 3. And also, if you take any cycle in your graph, which contains a vertex with degree 2, yeah, you also have to see at least, say, 3 of vertices of degree at least 3. It just means that you have to see sufficiently often vertices with degree at least 3. And then we show that if you take a small set of vertices, S, then they can't induce more edges than the number of vertices. This is something somehow quite standard argument. And then for large subgraphs, if they're connected, then majority of the vertices must have degree at least 3. The set of vertices with degree 2 or 1 is only epsilon fraction. Epsilon can be chosen in advance to be something very small. And the small and the large, I don't really want to define here. They are technical. It's some functional of the degree sequence. But roughly speaking, they are log of n. Okay. Okay, so 2 and 3 immediately implies the following. If you take a connected subgraph that contains more edges than vertices, then it means it can be small, so it must be large. And if it is large, it means that the set of vertices of degree 1 or 2 there must be small. So most of the vertices must be of degree at least 3 or more. Okay, so here's step 4. But before I say what step 4 is doing, I just want to quickly give you an idea why it's enough to actually show there's no permutation, or basically say that the graph has to be asymmetric. So you take a vertex, say, with degree 1, okay, and then you look at the assume I have a permutation sigma that is automorphism. So you look at the neighbors, and then the V is mapped by sigma to some other vertex. Because it's automorphism, you actually see exactly the same structure when you explore the neighborhood. And if you see sufficiently number of vertices with degree 3, then somehow when you meet a vertex that are fixed, you will eventually create, at least 2 cycles. You can draw a little bit, and you will quickly see that by the symmetry, you will have to see enough cycles. So what I wanted to show is that I will be able to find a connected subgraph with more edges than the number of vertices. That's my goal. But there are a lot of cases. So for instance, then maybe you say, okay, then the best case is I don't see vertices with degree 3. How about I just see degree of vertices 2, and I keep going like this until I see something fixed. And then the image of that on the map sigma must be the same structure. But now you will see this is the path where the ends are vertex with degree 1, and there's only one vertex with degree at least 3 or more than 2. And we in our previous slides, we already say such structure doesn't appear in random graphs. But there are other structures where the path actually can be fixed by this permutation. V can be mapped here, and this mapped here, this mapped here. But again, this is the path, so there must be some vertex here with degree 3, and then start to explore the neighborhood of those degree 3 vertices until you meet something that's fixed. Eventually, you will also see a lot of cycles. And the same thing happens with vertices with degree 2. So this map to here, this map to here, these are of degree 2. Maybe they meet somewhere that's a fixed vertex here. You see a cycle. But previously we say there's no cycle here with all vertices degree 2 over there. So there must be vertex here with degree 3, and then you start to explore neighborhood. Eventually we'll see another cycle here. So now you see 2 cycles again. So in any situation you see, you will find 2 cycles at least. But the situation is there are so many cases that it's almost impossible to just do case-by-case analysis. And that explains that why we have a statement 4 here. It's just try to get a statement that's clean enough, that's not too messy. So what we show is with high probability, if you take any automorphism sigma, then every vertex V that are moved and of degree 1 or 2 must lie in a connected subgraph that has more edges than vertices, and also it meets at most 3 vertices that are of degree at least 3 and are fixed. And the proof is by some kind of argument I showed before, somehow searching from those vertex, do some kind of depth first search until you see fixed vertex and then do something. Okay, and now it's the final step. So suppose you have a sigma like that. Okay, then using the previous step, I find a connected subgraph H of V. I delete all degree 1 vertices, basically trim off the tree attached to it, leaf attached to it, and then I get another subgraph. And then I take all the union over V that of degree 2, okay? And then I get just a graph with a few components, but the key part is every component you have more edges than vertices, and there are very few vertices with degree at least 3 and are fixed. So now you look at the set of vertices at least degree 3 in this component. It's the whole set of vertices, subtracting the set of vertices with degree 2 and the vertices with degree 3, but fixed. And then there are only 3 vertices over here. And this is a small proportion over here because it's a kinetic subgraph with more edges than vertices, so it's big. Because it's big, the set of vertices with degree 2 is a small proportion. So immediately you have shown that the set of vertices that are moved of degree 2 is less than 0.1 times the total set of vertices moved that are of degree RV3. That just says that with high probability, you don't get any commutation like this for degree 2, and then degree 1 you can treat similarly. And that finishes the proof. Okay, so I just want to quickly say what can be done further. I think the condition for asymmetry is not necessary, so we didn't really catch the threshold when delta goes to infinite. So when delta grows, this condition is also not necessary. It's only sufficient condition. And the reason is because we use this bound. Probability of UV and edge between UV conditioning our set of edges already being there. We use this bound, but of course this probability has to be dependent on the degree of U, degree of V, instead of just putting the upper bound of the degrees over here. When delta is bounded, this is at least of the right order of the probability, but when delta grows, this is just very wrong. And that's the reason we couldn't catch the threshold. But on the other hand, I believe with some condition on, still some constraints on delta, this constraint over here actually is necessary. So I think this is the right characterization of the asymmetry of random graphs with given degrees, but we were not able to prove this. And in fact, we have shown some kind of coincidence between the symmetry and the connectivity. Connectivity is easier to prove, but it's interesting to actually know that the connectivity threshold for GND is not known. It's open. So if anyone wants to try it, maybe this is something that obviously should be tried first. There are some known results, and it's not difficult to improve it because they didn't, in their proof, they didn't really try to optimize choices of certain constants and so on, but really trying to get a characterization that works for all degree sequences is very challenging as well. So that's my talk. Thank you very much.
Okay, let's thank Jane for a clear talk. And with that, maybe we can open it up to questions from the audience. So maybe I can get us started. I mean, the your work says something about this asymmetry and the degree sequences that lead to asymmetry for random graphs. But we also know there's a lot of interest in studying the computational complexity and sort of algorithms for graph isomorphism in the worst case. Are there interesting, like, random case graph isomorphism or automorphism problems where it doesn't take it's not symmetric or asymmetric with probability 1, but instead that you could have some interesting algorithm?
Yes. Well, in short, I think random graph isomorphism is easy.
Sure, but I guess my question is whether or not you consider these ensembles where you have degree sequences and so on. And so, like, my question is, have you encountered an ensemble where it's not just either one or the other with probability 1, or is there some reason why that
Oh, you mean why it's always either probability 0 or 1?
Is that always the case? Is there always
usually it's the case. If it's not, usually it's some situation. No, I mean, if you're talking about an algorithm that works or not,
I guess I'm just wondering whether or not there are random ensembles where you have non-zero measure of both asymmetric and symmetric.
oh yeah, sure. Well, even this result, it does have the situation where there's non-trivial probability. So I'll maybe go to the this one is easier to read. So if say the number of vertices with degree 2 is linear in n, because it can't be of more than n, right? So in that situation, it is, in fact, it's a non-trivial probability. It's some the probability of being symmetric is strictly between 0 and 1.
Thanks.
Yeah.
Are there other questions for Jane? Well, if not, let's thank Jane again, and we can proceed to the virtual grad house portion of this this Friday.